Hi there, we're talking about local linearity today. We're comparing complex valued functions and real valued functions. So for a normal function from the real numbers to the real numbers, we like to plot the function on xy axes. So we put an x-axis, which is a variable that ranges through the real numbers, and a y-axis, which of course is another variable that ranges through the real numbers. And then we plot them on a graph, which is then r cross r, right? The entire graph onto which the function is plotted is r cross r, and this is the set of xy pairs for which f of x equals y. Um, we have a local linearity phenomenon here. If we zoom in really close to any point, then locally this function starts to look a lot like a straight line, which of course is the tangent line to its curve. The job of the derivative is to measure the slope of that line. Now, graphically on the complex numbers, this is much harder to understand because these graphs don't transfer very well to the complex situation. In order to even plot the domain of a complex valued function, we need a real line and an imaginary line, and we create this space, which is, in a sense, r cross r, but it's not the domain cross the range of a complex valued function from the complex numbers to itself. It's in fact merely the domain of that function, which means we need two more dimensions in order to plot the graph of the function. So in order to draw a proper graph of a complex function, we essentially need four real dimensions, and I need a lot more than a whiteboard. So this gives us an immediate difficulty here. In order to understand the way these functions operate geometrically, we can't graph them very well. We need to think about their domains. We're going to reason by analogy, and we're going to shrink our perception of the real case into a small enough view so that we can understand what's happening in the real case only by looking at the domain. So let's do that next. So let's pretend that the whiteboard was briefly one-dimensional, and we could only represent the domain of the function, which of course is going to be the real line. So we have f mapping from the reals to the reals, but we don't have a representation of the codomain of that function. So how would we represent this function? Well, we could say y equals f of x, but these are only the x values here. Now, if the function was arbitrary, then it's very hard to represent it here. But you can imagine each x value here maps to some y value, which then, because we only have one dimension of view, has to be represented on the same line. That would mean that from this point of view, we would regard the function to be a motion within the real line. It might be shifting the points downwards this way, or shifting them this way, or doing something completely different. So for example, the absolute value function maps this x to itself, but it maps this x over here to its absolute value, and it maps 0 to itself, and this goes to itself. But these things jump far over the origin, etc. So the absolute value function can be viewed not as its traditional graph like this, but as a transformation that happens to this one-dimensional picture. Namely, it gets folded over this way. Now that fold does something interesting at 0. It sort of kinks it up there at 0, and that's the reason why the absolute value function is not differentiable at 0. It's hard to distinguish in this view the absolute value function from the parabola because, well, their graphs are similar, and they both have codomains which are only the non-negative reals. So the parabola also folds it over, but does so in a slightly different way. And geometrically, it's very similar to what we have over here. So we're going to try to perceive our functions as operating on a one-dimensional space and moving it to itself. We're basically reusing the domain and codomain in this picture because that's what we'll have to do in the complex case. So what does local linearity mean from this point of view? Local linearity means locally the function is very like a linear function. So let's examine what a linear function looks like from this point of view where we can only see its domain x. So let's imagine f of x equals mx plus b. Well, a linear function, of course, is a composition of a multiplication by constant function and an addition of a scalar function. And so if we can understand the geometry of both of those parts from this point of view, then we'll be just fine and we'll be able to understand the geometry of a linear function on the real line. So what does multiplication by a constant do from this point of view? If we take every real number x and multiply it by, for example, 2, then 1 goes to 2, 2 goes to 4, 3 goes to 6, 0 goes to 0, -1 goes to -2, and we see this is just an expansion. It expands evenly by a factor of 2 all of the real numbers outward from the origin. The origin stays fixed. If we have m equals 1/2, then this is a contraction. If we have m equals 10, it's an expansion by a factor of 10. And if we have m equals 1, we could call that an expansion by a factor of 1, but really it's a kind of, well, it's the identity map here. So the m here gives us geometric expansion or contraction if it's less than 1. I should clarify here that m can be negative, and if m is negative, a negative expansion is of course going to be a flip over the axis. So 1 will go to -1, and everything will get reversed or mirror imaged. The b, of course, is even simpler geometrically. The b is just a shift. So a linear function from this point of view has the geometry of expanding the numbers and shifting their distance between them, but uniformly so, and then shifting them along this single axis here. From that point of view, then we can understand local linearity. So local linearity means that locally any function is doing something like this, something similar to this. So if we look at the parabola, for example, the parabola has this very complicated structure, but nearby any point, all of the values are getting stretched a little bit and moved a little bit. Maybe reversed if the m value is negative, but they're getting stretched a little bit and they're getting moved a little bit along the x-axis. So basically, this explanation for the function, that it is a stretch followed by a shift, is locally approximately true for all the points, even if the function is not linear. So this is a one-dimensional perspective on what local linearity means for real-valued functions. And we're going to try to take an analogous perspective here because we cannot easily graph these functions in 2 dimensions. So these functions are going to be regarded as taking this as their domain and taking also this as their codomain, and we're going to think about them geometrically in those terms. So let's get started. What does it mean then for a complex valued function to be linear? Well, if we have a linear function, then again we have f of z equals mz plus b. Now, here I'm using z instead of x for a complex variable, but it doesn't really make much difference. Here I'm using m and b as the slope and intercept, I suppose, of the complex function, but we need to understand here that m and b might be not only positive or negative numbers, they may be complex numbers themselves. So in order to understand the geometry of a linear function from c to c, we just need to understand the geometry of these 2 parts, the multiplication by m and the addition of b. Well, neither one of those is particularly hard. It'll be easier to understand the multiplication by m if we convert m itself to polar coordinates. So f of z, as we've seen, any complex number can be written in the form non-negative real constant times cis of theta. So we'll write m0 times cis of theta. In other courses, this is what we might write e to the I theta here instead of cis. So that's the modulus of m right here, and then cis of the argument of m, and then we're going to multiply that by z, and then add b. So now this is two multiplications now, but one of them is a multiplication by a complex number whose modulus is 1, and one of them is a multiplication by a non-negative real number, m0, which is the modulus of m. Then we have the addition by b. We just need to understand all of these three parts now in terms of the geometry of the complex numbers. So let's identify the geometry of each part. So multiplication by cis theta is simply going to change the argument of the complex number, and this is going to be a rotation and around the origin. So when we multiply complex numbers, the arguments add and the moduli multiply. So here we're multiplying by something that has a modulus of 1 and has an argument of theta, and that's just going to accomplish a rotation. So a uniform rotation around the origin. So the complex numbers are getting rotated this way. If theta is pi, they get rotated fully 180 degrees, or pi radians. And if theta is any other value, they just rotate here. Next, we're multiplying by m naught. So what does that do geometrically? Multiplication by m naught. Now, m naught is the modulus of m here, and it's a non-negative real number. And so when we multiply the complex numbers by a non-negative real, what happens is this whole picture just gets stretched or dilated uniformly in all directions. So if m naught is 2, then everything gets twice as far from the origin. Everything just moves out. Now, you may be worried about what if it's negative, but it can't be negative because it's the modulus of m. If it could be 0 in theory, and then that would just collapse all the points to the origin because we're just multiplying by 0. So we have a multiplication by cis theta, which accomplishes a rotation, and a multiplication by m naught, which accomplishes a dilation. Finally, we have the addition of b, which has a very simple geometric significance here, and that is a shift. Now, b could be positive, b could be negative, it could move rightward, it could be leftward, but those aren't the only options for b because it's a complex number. It could be a positive imaginary, negative imaginary, or some mix. But one way or another, we're shifting in 2 dimensions by a vector b. So the entire complex plane is moving this way or moving this way or moving when we add this b. So taken together, we have a rotation around the origin, a uniform dilation, followed by a shift by b. And so all of the complex numbers are moving according to these actions. Now that's local linearity, and that's what we expect when the function has a derivative. Now, well, that's the case of the linear function. Local linearity means that the functions will be approximately doing this. Now, what you should notice about all of these operations is that there are things you cannot do by combining these operations. For example, there's no way to combine a rotation by an angle and a uniform dilation and a shift and end up with a mirror reflection. And so that means that, oddly, the mirror reflection, which is the conjugate map, cannot be accomplished like this. And that means the conjugation map is not a linear map. And that might be a bit surprising. There's no m, so that f of z equals mz plus b. There's no m and b, so that formula will give you z bar. And what we'll see later is that the conjugation map, z goes to z bar, is not even a differentiable map, which is surprising because it's a very important map and it's a continuous map and it seems to have very nice properties, but it's not differentiable because it doesn't have the right geometry for it. Any function which is differentiable will be locally approximately linear, which means that it will be locally obeying approximately these things. And so locally, we won't see certain phenomenon in these differentiable functions on the complex plane. We won't see phenomenon like mirror reflections, even locally. We won't see phenomenon like, squishing in one direction, but stretching in another direction, because you can't get that from the geometry of these things. We won't see shearing phenomenon where this line moves this way, but this line moves this way. basically all of the phenomena that we will see are those that preserve the angles. And that's, we tend to use the word conformal for that geometric property, that the angles are getting conserved. So if something is getting squished in one direction, it can be contracted and in all directions and still be locally linear and still be complex differentiable, but it won't be squished in one direction and stretched out in another direction in a way that would change the angles between certain lines or rays. So that's the expectation of the geometry of locally linear functions on the complex plane.